Hey now, it's Jason Thide coming at you live, except pre-recorded, so not live, and we are looking at trigonometric equations. This is our last trig topic, which is pretty sad overall, but it's okay because we can always go back and review them to our heart's content. We're going to be looking at a ton of different types of trig equations, or at least a few. And our first one will be first degree ones. So when we talk about first degree trig equations, it's kind of related to looking at first degree equations for polynomials, for example, solving something like that, for example, is a first degree polynomial equation because the degree on x is 1. And you could also have, say, a second degree equation, something like that, for example. That would be a second degree equation. But we are playing with trig equations specifically. So instead of just a straight up variable, that variable is going to be within a trig function. And that's what we're going to be dealing with at first. There's a ton of ways to do this. Worth noting is that we're going to be encountering some questions for which you have to use a calculator and some questions that can be done without a calculator. But generally speaking, you want to find the reference angle, your theta r, and then use that to find the values of theta, perhaps using the cast rule in whatever quadrants we need. So something like this. If 2 sine of x minus 3 equals negative 2, we are going to isolate x. In order to do that, we need to isolate sine x. So 2 sine x minus 3 equals negative 2. Of course, this is a type of equation that we have done in previous units, but it's good for us to just use this one as a bit of a warm-up. So we're going to solve that. We're going to add 3 to both sides so that 2 sine x is equal to 1, and then divide both sides by 2. Sine x is equal to 1/2. Now, using special triangles, if this is like pi over 6, and this is pi over 3, we can note then that our reference angle, or xr in this case, would be pi over 6, except we should note what our format is, our units are for the angle for our final answer. Notice here, we're told it's from 0 degrees to 360 degrees. So rather than stating this in radians, we should probably be stating this in degrees. So 30 degrees is what we're after. And then you can phrase your special triangle a different way. Or if you have a different way of getting the value of x based on sine x being 1/2, that's cool. You follow your heart. Unit circle maybe, whatever it is you want to do. But this is a key component. So getting to that step is basically part of the marks here. Then we can play with cast rule. Boof, 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 boof. Sine of x is positive, which happens in these quadrants. And in quadrant 1, x would be 30 degrees. And in quadrant 2, x would be 150 degrees. Therefore, our solution between 0 and 360 we can say includes 30 degrees and 150 degrees. Boom, done. You're welcome to try this next one if you want. Do note that it does require a calculator. Process-wise, we're still pretty much same. The only trick will be dealing with this business, right? Sine of x equals 1/2 we could do without a calculator because it was linked to a special triangle, but we might see something different in this equation. If you want to pause, give it a try, wicked awesome. If not, also cool. Here's what I would do. I would say for cos of x plus 5 equals 2, I would say that 4 cos of x is negative 3, and thus the cosine of x is negative 3 over 4. Now, remember that when you get the reference angle and you've got a negative ratio, you're going to plug that into your calculator positive-wise. So for the reference angle, xr, we're going to take the inverse cosine of positive 3 over 4. And that's to ensure that what we get is in the first quadrant. If we don't put that there, if we take this negative 3 over 4, then we're going to get something that's in a different quadrant, which won't really be as helpful for us for actually finding what it could be in other quadrants. So always the positive version, don't forget that. Reference angle is, oh, I gotta use my calculator. Inverse cosine of 3 over 4. Now, in degrees, that's 41.4-ish degrees, or we know to go to 3 decimal places. Oops. Which would be that. Oh, whoops. There. That's what it would be, to 3 decimal places. Except note that we're dealing with radians. Ugh. So having this as 41-ish degrees doesn't make sense. So we make sure our calculator is in radians mode. And then we calculate it. And in radians, this 41.4-ish degrees is actually 0.723-ish. That is the reference angle. How do we find the other ones? You can use the cast rule again. We're dealing with where cosine is negative, which is quadrants 2 and 3. Over here, we need to take pi minus the reference angle. Over here, we need to take pi plus the reference angle. And we get values for that. So when I take pi and I subtract that x sub r, pi minus my answer is 2.419-ish to 3 decimal places. And then if I take that, or if I take pi plus my reference angle, plus pi, I get 3.864. It doesn't look so pretty, right? We're used to maybe having things work out with a nice pi over 6 or something. These ones don't, but that's because of us having to use a calculator, because this was not a special ratio linked to one of our special angles or special triangles. So that's that. That's that answer. Quick, try this last one. Ooh, this is a non-calculator one. Okay. Hopefully you've paused, you've tried it. Here I go. 3 cosecant x plus 1 is 2. Okay. 3 cosecant x is 1. The cosecant of x is thus a third. And I don't have a cosecant button on my calculator, but fortunately, I guess it's a non-calculator anyways. But anyways, I know that's related to sine x, and thus sine x is the reciprocal, so sine x is 3. Whoa! I know, and there's a bunch of ways for me to back this up, but I know that sine of x has to be between 0 and 1. So as soon as I get this, I'm saying no solution. That's that. So that's kind of the intro part of it. Now, we could have other domains. Those other ones were from 0 to 2 pi or 0 to 360 degrees. But looking at a question like this one says x could be anywhere from 0 to 6 pi. And in a case like that, we'll get our initial answers from the initial quadrants that we select for our solutions, but then find anything coterminal to those that is within this particular span. So initially, everything's still same. We've got that 2 sine x equals root 2. Divide both sides by 2. Wicked. And from special angles, I know that this means I have a reference angle of 45 degrees or pi over 4. Neat. From the cast rule, I know that I'm dealing in quadrants where sine of x is positive, so that's quadrants 1 and 2. And in quadrant 1, that's just straight up pi over 4. And in quadrant 2, that's 3 pi over 4. Those are both acceptable answers for this, right? They are in this domain. They are between 0 and 6 pi. And I can start writing them in here. I can say that x could be pi over 4, if this pen starts working again. And it could be, are you serious right now? Sorry, everyone. And it could be 3 pi over 4. But also anything coterminal to that, as long as it's still less than 6 pi and more than 0. So I'm going to add things. So I'm going to take this, I'm going to add 2 pi, which would be 8 pi over 4. So that is 9 pi over 4 for the angle. And similarly, I'm going to add 8 pi over 4 to this, which will get me 11 pi over 4. And I can keep doing this. I can keep adding 2 pi. I can keep adding 2 pi and see where it gets me. That'll be 17 pi over 4. And this one would be 19 pi over 4. And you can continue checking to see whether you're within bounds. 19 pi over 4 is, well, 19 over 4 is a little less than 5, so we're a little less than 5 pi. And if we tried to add another 2 pi to this, we'd get to 25 pi over 4. But 25 over 4 is a little more than 6. So this would be out of bounds. We can't use that. 19 pi over 4 was the last one we could use. So that's where we'll close this set. What's that? Quick! Try the others. There's no time. There's plenty of time, but try them. Calculator and calculator. See what you get. And see how it compares to whatever I get. 2 cosine Okay. I get that. Gosh, I hope it's correct. And then I get that. So my reference angle is in degrees. Let's make sure my calculator is actually in degrees mode, which would be a common mistake. Oops. 5 over 7. I'm getting 44.415 degrees. Cosine is positive, so we're here, we're here. What could my values be? It could be 44.415. That's an option. It could also be the quadrant 4 version of this. So I take that and I subtract it from 360 to get me 315.585 degrees. But then we can go as low as negative 360. So we can't go any higher here. We're not going to add 360 degrees. That's silly because we've already reached our maximum. But we can subtract. In fact, we could subtract just once. We're going one whole revolution lower than 0. So 44.415 minus 360 degrees to get something coterminal to it would be negative 315.585 degrees. And 315.585 degrees minus 360 to again get something coterminal to it would there give us 44.415 degrees. So note that we've got 4 possible answers over 2 revolutions. Where over here, if it's just over 1 revolution, you're looking at 2 answers. So things to note with those connections, right? Had no solution. But 1 revolution, 2 possible answers because of the 2 possible quadrants. Here we have 3 revolutions. 3 times 2 is 6. We have 6 solutions there. Connections like that, worth knowing. Anyways, this question here, 4 tan x minus 1 is 2 tan x plus 3. So 2 tan x is 4. Neat. Tan x is 2. We are in radians. Oh, the calculator is switching. At least it's good practice, the calculator switching. My reference angle is inverse tan of 2, which is 1.107. That's radians. Don't forget. Looks like I'm dealing with quadrants 1 and 3. So in quadrant 1, this would be 1.107. And in quadrant 3, it'd be that plus pi, which would be 4.249. I could start putting in answers here, like the 1.107 and the 4.249. But, whoa, the lower bound on this is 2 pi. These are not at least 2 pi. What's 2 pi? Like at least 6. So we're not going from 0 to something. We're not saying 0 is less than or equal to x is less than or equal to something else. We're starting at 2 pi as our baseline. So these aren't actually our starting ones. So do be careful of that. But we'll just add 2 pi to each of these. And that'll be good. So if our original took us from 0 to 2 pi, we just add 2 pi to everything. And then we'll be going from 2 pi to 4 pi. So that's it. Boop, pop. So 1.107 plus 2 pi gives me 7.390. And then this other one, 4.249 plus 2 pi should be in the neighborhood of 10-ish. My calculator says that it is 10.532. One other thing worth noting is you're going to want to keep things as exact as possible. So this wasn't exactly 1.107, so you want to keep things as accurate as possible to 3 decimal places. So it wasn't exactly 1.107, it was, I don't know, what was it? Show me tan inverse of 2. It was 1.107, 1487, etc., etc. And pi isn't exactly 3.141, right? It's got a whole bunch of digits after that. So just keep things, keep this full 1.107, 148, etc. in your calculator, or write down all its digits here, 1487118, so that when you add it to pi, you can ensure that this last digit is still accurate. If it's not, then it would be a rounding error, and that would be just unfortunate. Whoop, pop. Last bit of things is a general solution. So we've talked about in previous units how to look at a general form of all coterminal angles to a specific angle, and that's where we add infinitely many 2 pi's, 2k pi's, 2 pi's. Where as long as we have some integer number of full revolutions being added to it, we're good. They're all coterminal. Right? If you have something like pi over 2, it's coterminal with 5 pi over 2, it's coterminal with 9 pi over 2, it's coterminal with 13 pi over 2, and so on and so forth. There's infinitely many. So general solution, we're looking for those infinitely many solutions to write down. Initially, starts off same way. We have to isolate x. We have to find that reference angle. Whoop. So sine of x is root 3 over 2. X is like 60 degrees, but we are in radians. So that's pi over 3, and that's my reference angle. Boop-bop. Looking at quadrants 1 and 2. In quadrant 1, we're talking about pi over 3. In quadrant 2, 2 pi over 3. So what could x be? It could be pi over 3. That's a gross pi. But it could also be anything coterminal to it. So we're going to add some multiple of 2 pi. Or it could also be 2 pi over 3. But it could also be anything coterminal to that. And of course, if we're introducing that k, we do have to say that k has to be, in this case, an integer. So we're adding some integer number of 2 pi, some integer number of revolutions. Do you know? Do you feel? Do you dig? Sure you do. There are 2 more questions here. I wouldn't be surprised if the next one requires a calculator, because it looks like it will. Maybe someone should have written that somewhere. So give it a try, give it a go, give it a stab, give it a whirl, give it a shot, and we'll see what happens. Doo-doo. I have to be in radians. I am in radians. That's nice. So I'm getting a reference angle of 0.983. It's more like 0.982793723, but that's what I've got for my rounded answer for now. If you want, because this isn't the final answer, you can put down the other parts of this, just if you want a few more digits of precision there. Anyways, I am dealing with negative quadrants for tan. Oops. So in quadrant 2, pi minus that is 2.159. And in quadrant 4, I need to take 2 pi minus that. 2 pi minus that answer is 5.300. And those are my answers, but those are my answers from 0 to 2 pi, so I need to make sure I include everything coterminal to it. So we add the 2k pi, add 2k pi, and we specify that k is an integer. How's that? And then this lastest one. All right. Secant of x is 3, which means that cosine of x is 1/3. I better switch back into degrees here. Inverse cosine of 1/3 is 70.529 degrees. Quadrant-wise, I'm dealing with a positive cosine, so I'm there and there. So I could be 70.529 degrees, or let me move this over. Or I could be 360 minus that, which is 289.471 degrees. But of course, I can be anything coterminal to those, so I need to make sure I add some multiple of 360 degrees to each one of those. And when we say a multiple, I specifically mean an integer multiple. So that's our intro into trig equations. We'll be looking at other kinds of equations as well. There is some practice on this next page. Some of these will be calculator ones, some of these will be less calculator. From the looks of things, these are actually all calculator ones, just based on the answers. Ooh. Well, have fun with those. Do also always make sure that your calculator is in the proper mode for the question you're solving, because if it's not, it's going to be an issue. If you have questions, comments, concerns, please do let me know. If you have any difficulty at all whatsoever, just message me, and it'll all be hunky-dory. But do make sure you have a good basis for solving first-degree trig equations. So as we proceed with the others, everything's wicked cool. That's all I've got. I will see you in the future. Tell everyone I say hello, and be good to yourselves. Always remember to be good to yourselves, and be good to one another, of course. The end.